So let's show the inverse of these two 2 by 2 matrices using theorem 1.4.5. When you look at, especially for the first matrix, it's a little bit complicated, so we might use a lot of spaces here. So let's deal with the second matrix a little bit later. So we have here this, and if I may, please, if it's okay, I'm just going to label this as a matrix E, and about this one F, so that I could represent their inverses later. Just like this one, the inverse of a matrix E is 1 over, pardon, let me do it again. We have 1 over AD, oh, yeah, that's AD minus BC times this one, D, A, negative B, and negative C, in this manner. So, same as here, the inverse of F is equal to 1 over AD minus BC times, we have here D, A, negative B, negative of C. So first, let's identify the correct representations for A, B, and C, and D. Of course, here, it's a very lengthy here for the first, plus e to the negative x. You might get tempted of distributing that 1/2 here, but you may also hold it for a while, because there might be some unique processes that will be included here later. So here you have e to the x minus e to the power of negative x. C is the same as b, e to the power of x, and then e to the negative x. And then your d is 1/2 e to the x plus e to the negative x. So let's start with AD minus BC, okay? Because that's the item we're going to input here. So let's start with AD first. A and D, we multiply these two, so you have 1/2 e to the x plus e to the negative x, just like this, to be multiplied by another 1/2 e to the x minus e to the negative x. We can take out the two 1/2, you'll have 1/4 here, 1/2 times 1/2, and multiply the terms using FOIL method, the two binomial expressions. So e to the x times this one, so I have e to the power of 2x, okay? So x plus x, 2x, add the exponents, right? Next, this one here and this, plus e negative x plus x power of 0. This is also the same as this 2, plus e to the power of 0 as well. Because that's e, add the exponents negative 1 and positive 1, so 0 e to the power of 0. It's not 0, but it's e to the power of 0, which would tell us that it's equal to 1. And finally, for the last, plus this 2, e to the power of negative 2x, because negative x, negative 2x. So AD, just for AD alone, I have 1/4 of e to the 2x. I could also write here e to the negative 2x. And since both of these are equal to 1, plus 2. Again, plus 2, because they are both equal to 1. That's for AD alone. Let's have BC here. BC, the only difference is the operation between the binomials, e to the x minus e to the negative x times another 1/2 e to the x e to the negative x. Can you check? B and C share the same operation separating the binomial. So same thing, 1/4 these two, e to the 2x, then the next one here and here, minus e to the 0. Minus because negative times positive, as well as here, positive is negative minus e to the 0. And then plus, because it's negative times negative, e to the negative 2x. Negative x plus negative x, just like that. So generally, it's 1/4 of e to the 2x, and then plus e to the negative 2x minus 2. This is 1, that's 1 as well. So we're a little bit farther already. The next here is to subtract both of them. Yeah, I still have space here. AD minus BC. So this is the entire result of AD. This is BC. So that's 1/4. Let me try to distribute. Or, yeah, a little bit later. E to the 2x plus e to the negative 2x plus 2 minus 1/4 BC. E to the 2x plus e to the negative 2x minus 2. So when we distribute the 1/4, I have 1/4 e to the 2x plus 1/4 e to the negative 2x. And 1/4 of 2 is plus 1/2 minus 1/4 e to the 2x negative minus 1/4 e to the negative 2x. Negative times negative plus 1/2. This is here. Cancel. Again, we have this same item here. We also have the same item here. In short, AD minus BC is just equal to 1. See? It's a very long process, but it's just equal to 1. Nevertheless, the purpose for that is to make sure that our process is correct. So when we return here in this formula, so it's just simply equal to 1/1 times these results here. Let me add this at the bottom, so I still have space for the second one beside it. Again, that's the entire so I have okay, it's probably I'm gonna use this area so that I would be scrolling up and down from time to time. So again, sorry, my bad, I have here is equal to 1/1, and then D, this one here, is actually the same as the previous. So they were just interchanged. 1/2 e to the x plus e to the negative x. Here as well, 1/2 e to the x plus e to the negative x. It's just that the next thing will happen here is your b will become negative and your c will become negative. So negative 1/2 e to the x minus e to the negative x, and negative 1/2 here as well, e to the x minus e to the negative x. Of course, finally, 1/2 e to the x plus e to the negative x, negative 1/2 e to the x minus e to the negative x, minus 1/2 e to the x minus e to the negative x, and then 1/2 e to the x plus e to the negative x. This is for the first matrix. Now for the second, since the spaces are no longer available, let me copy it here. Cosine theta, sine theta, negative sine theta, cosine theta. I coined it F, and I'm going to get its inverse. So you have 1/AD minus BC, DA minus B minus C. So let's start with AD minus BC. And since it's unlike the first one, that's very long, we can just simply combine them. A is cosine theta, D is cosine theta, minus B is sine theta, times C, which is negative sine theta. We have cosine squared theta plus sine squared theta. Remember, dear trigo, AD minus BC is also equal to 1. The sum of cosine squared theta and sine squared theta is just 1. So here, well, of course, it's not an assurance that if we have examples like this soon, it's always, or the determinant is always equal to 1. Just for this example alone. So negative 1/1 times interchange. So it's the cosine theta here. The negative here will become negative sine theta. And the negative of c, which is already a negative trigonometric function, you will have here positive sine theta. So the final answer is just simply cosine theta negative. Let's try to write this not so confusing, just like that, theta, and here is positive sine theta. This is the inverse of the second 2x2 matrix. So as you can see, you followed theorem 1.4.5 in order for us to solve for these two. And thank you for watching.